A graduate student was analyzing old data from a radio telescope in Australia when he found something impossible. A signal, brief, violent, unexplainable, in less than 5 milliseconds faster than you can blink something in deep space, released more energy than our sun produces in an entire day. The signal traveled 3 billion light-years and still hit our telescopes like a cosmic thunderclap. Then, silence. Scientists didn't believe it was real. They thought it was a glitch, interference, maybe a microwave oven. But it wasn't. This was the first fast radio burst, one of the most mysterious phenomena in the universe. Today, we're uncovering what these explosions are, where they come from, the theories competing to explain them, and what they reveal about the cosmos, and possibly whether we're alone. Because the truth might be stranger than science fiction. So what exactly are fast radio bursts? Imagine a cosmic camera flash that outshines an entire galaxy, but instead of visible light, it's radio waves. And instead of lasting a fraction of a second, it lasts just 1 to 5 milliseconds. That's 20 times faster than you can blink the energy. A single burst releases what 500 million suns would produce, concentrated into those few milliseconds. And they're coming from billions of light-years away. The story begins in the early 2000s. The Parkes Observatory in Australia was constantly recording the sky. Astrophysicist Duncan Lorimer gave some old data to his student, David Narkovic, as a project. David found a signal from August 2001 that shouldn't exist. Impossibly bright, impossibly brief, impossibly distant. But when something seems impossible, scientists get skeptical. For years, they debated whether the Lorimer burst was even real. Could it be interference? A satellite? Someone's microwave oven? It wasn't until 2013, when more bursts were discovered, that the truth became undeniable. These cosmic explosions were real, but accepting they're real only opened bigger questions. Fast radio bursts are completely unpredictable. We can't forecast when or where they'll happen. They're absurdly brief when most cosmic events last minutes, hours, or days. The physics required is extreme, and for almost a decade, we had no idea what caused them. Then came something stranger. Some fast radio bursts repeat from the same location. Others flash once and never again. Why? Most come from distant galaxies billions of light-years away. But in 2020, we detected one right here in our Milky Way. To solve this mystery, we needed to detect them in real time and catch them in the act. But how do you detect something that lasts less than a heartbeat and comes from billions of light-years away? Detecting fast radio bursts is almost as impressive as the bursts themselves. Imagine standing on a beach in California while someone whispers your name from Japan, but there are hundreds of radio stations broadcasting at full volume and a thunderstorm raging around you. That's what radio astronomers face. This is where radio telescopes come in. Sigmy in Canada looks like a massive skateboard park but monitors the entire northern sky simultaneously. Parkes in Australia, where it all began, still scans the southern skies. FAST in China is the largest single-dish telescope on Earth, big enough to fit 30 football fields inside. These observatories face one enormous challenge: distinguishing real cosmic signals from interference. Your cell phone, your car, even solar panels create radio noise. The answer lies in the physics of the signal itself. When radio waves travel through space, they pass through ionized gas between galaxies. This plasma causes different frequencies to arrive at slightly different times. We call this dispersion. The amount of dispersion tells us the distance. It's like a cosmic odometer. When scientists measured the Lorimer burst's dispersion, the numbers proved it came from outside our galaxy, way outside, billions of light-years. Now, the energy. A single fast radio burst releases what 500 million suns would produce, concentrated into milliseconds. If you could capture just one burst and convert it to electricity, you could power Earth for trillions of years. And they're happening constantly. Scientists estimate thousands occur across the observable universe every single day. But we only catch a tiny fraction. Most happen when we're not watching. Most are too distant. Some occur during the day when the sun's interference drowns them out. Modern systems now detect bursts in real time, triggering alerts that send telescopes worldwide swiveling to the same spot. It's a global effort. The more telescopes that see the same burst, the more precisely we locate its source. And that precision That's what finally allowed us to start solving the mystery. Once we knew how to detect fast radio bursts reliably, discoveries accelerated. 2007, Duncan Lorimer publishes the first burst. Scientific community is skeptical. 2012, more bursts discovered in real time. Skepticism fades, these are real. 2016, the breakthrough. A fast radio burst designated FRB 121,100 to did something unexpected, it repeated. Burst after burst from the exact same location. This changed everything. A one-time burst is impossible to study in detail. You get one snapshot, then it's gone forever. But a repeating source, that's a gift. You can watch it over time, study its behavior, understand its environment. Scientists traced FRB 121,102 to a dwarf galaxy 3 billion light-years away, a factory for new stars. Something in that galaxy was producing hundreds of bursts. The environment was extreme. Strong magnetic fields, dense gas, intense radiation. This told scientists something crucial. Whatever makes these bursts survives in one of the harshest environments in the universe. But it also created a puzzle. If some bursts repeat, why don't others? Were there different types of sources? 2019, Chime starts detecting dozens of bursts in months. More than doubling our catalog. Some repeated, some didn't, some came from nearby galaxies, others from the edge of the universe. But we still couldn't point to a specific object and say, that's what's creating these bursts. Until April 28, 2020, multiple telescopes worldwide detected the same event simultaneously, a fast radio burst from inside our own galaxy, only 30,000 light-years away, practically our cosmic backyard. And for the first time, we knew exactly what produced it, a magnetar. And on that day, it produced a fast radio burst. This was the smoking gun. Direct evidence linking fast radio bursts to a specific cosmic object. The detection was confirmed worldwide, no doubt. We finally had our answer, or at least part of it. Because this burst was weaker than the extragalactic ones, the environment was different. This suggested something important. There might not be one explanation. There might be several different sources, different mechanisms, all producing similar signals. The mystery hadn't been solved. It had evolved. We now knew magnetars could produce fast radio bursts. But were all bursts from magnetars? Why did they behave so differently? To answer these questions, we need to examine the leading theories. Naraka for 30 to 630 scientists have proposed over 50 explanations for fast radio bursts. But as evidence accumulated, the field narrowed to a few leading contenders. Let's start with the frontrunner, magnetars. To understand fast radio bursts, you need to understand these objects. Take a star 20 times more massive than our Sun. When it explodes in a supernova, what's left is a core compressed into a sphere the size of a city containing more mass than our entire Sun. Now add rotation. The collapsing core spins hundreds of times per second, creating a magnetic field a quadrillion times stronger than Earth's, strong enough to erase every credit card on the planet from the Moon's distance, strong enough to pull iron from your blood. These are magnetars. Only 30 are known in our galaxy. How do they produce fast radio bursts? The magnetar's crust is under tremendous stress from those impossibly powerful magnetic fields. Eventually, it fractures a starquake. The magnetic field lines break and reconnect, accelerating particles to near light speed and generating intense beams of radio waves. If a beam points toward Earth, we see a fast radio burst. The evidence is compelling. We detected that burst from SGR 1935 plus 2154. Magnetars exist, can produce the required energy, and repeating bursts come from environments matching young magnetars. But there are problems. Not all bursts fit the profile. Some come from galaxies with few young stars. Some are more energetic than expected. And why do some repeat while others don't? This brings us to the second theory, stellar collisions. Imagine two neutron stars locked in a death spiral. Over millions of years, they spiral closer until they collide. The collision releases more energy than all stars in the observable universe combined, creating gravitational waves and potentially fast radio bursts. This explains one-time burst events that destroy themselves. Neutron stars colliding with black holes or special supernovas creating magnetars could also produce bursts as a birth cry. The collision theory explains non-repeating bursts. But it doesn't explain repeaters like FRB 121102, which has produced hundreds of bursts over years. Third theory, supermassive black holes. At most galaxy centers lurks a supermassive black hole. When matter falls toward them, it forms a swirling disk that heats 2 millions of degrees. Sometimes black holes launch jet beams of particles shooting out at nearly light speed. Could these jets produce fast radio bursts? The magnetic fields near black holes are enormously powerful. Matter falling in could create shocks generating radio wave bursts. Several bursts have been traced to galaxies with active black holes. But most don't come from active galaxies, and the precise mechanism remains unclear. Beyond these, there are exotic scenarios, pulsars in tight orbits, strange matter from the Big Bang, even cosmic strings theoretical defects in spacetime itself. Science explores all possibilities, even unlikely ones, because sometimes the universe surprises us. But there's one more theory we need to address. It's controversial, unlikely, but we can't completely rule it out. Could fast radio bursts be artificial? Could they be technology? Avi Loeb, an astrophysicist at Harvard, has proposed that some bursts could be leakage from enormous power generators used by advanced alien civilizations to propel spacecraft. The concept, instead of carrying fuel, you build a massive power station generating an intense energy beam. This beam hits a light sail on your spacecraft, pushing it to a fraction of light speed. If Earth happened to be in the way of that beam, we detect it as a fast radio burst. The numbers actually work. To push a large payload across interstellar distances requires roughly the energy we observe in fast radio bursts. But let's be clear, the vast majority of scientists don't think this is what fast radio bursts are. The consensus strongly favors natural explanations, particularly magnetars. Here's why we can't dismiss it entirely, though. History. In 1967, when Jocelyn Bell discovered pulsars, scientists briefly considered they might be artificial. They even called the first one little green men. They quickly realized pulsars were natural, but considering the possibility was scientifically responsible. Also, SETI monitors fast radio bursts for artificial patterns. If there's even a small chance, it's worth checking. But applying Occam's razor, the simplest explanation, is usually correct. We know magnetars exist and can produce these bursts. We don't need aliens to explain what we're seeing. Invoking aliens requires assuming technological civilizations exist. They've developed this propulsion. They're using it frequently enough for us to detect thousands of times, and we're positioned to see these beams. That's many assumptions. The scientific approach: pursue the most likely explanations vigorously while keeping an open mind. The universe has surprised us before. Whatever fast radio bursts are, magnetar starquakes, collisions, or something unexpected, they're revealing cosmic secrets we never imagined. And here's the exciting part: regardless of what causes them, fast radio bursts have become one of the most powerful tools in modern astronomy. Even though we're still figuring out what causes all fast radio bursts, we're already using them to solve major cosmic mysteries. For decades, astronomers had a frustrating problem. When they calculated how much normal matter should exist based on the Big Bang, the numbers didn't match observations. About half the universe's normal matter was missing. Where was it? In the space between galaxies, extremely hot, diffuse ionized gas floating in the cosmic web. So thin and hot, it's essentially invisible. Fast radio bursts solved this. Remember dispersion? We can measure exactly how much ionized gas a burst traveled through. Since we know the distance, we can calculate the gas density. It's like using fog to see invisible laser beams. Using fast radio bursts, astronomers finally mapped this missing matter, confirming it's exactly where models predicted. A decades-old mystery solved. But there's more. Fast radio bursts are helping measure the universe's expansion. Right now, different methods give different answers. The Hubble tension. Fast radio bursts offer an independent measurement method that might resolve this. They also let us study extreme physics impossible on Earth. Magnetic fields 1 trillion times stronger than anything in our laboratories. Densities exceeding our technology. Every fast radio burst is a natural laboratory testing physics at the absolute edge of what's possible. Scientists use them to test Einstein's relativity in extreme environments and understand matter at densities where atomic nuclei touch. This is why fast radio bursts matter so much. They're not just puzzles, they're tools to understand the universe itself. Windows into cosmic history, laboratories for extreme physics, and maps of the invisible universe. And we're just getting started. If you think what we've discovered is impressive, wait until you hear what's coming. We're on the verge of a revolution in fast radio burst astronomy. The Square Kilometer Array SKA will be the largest radio telescope ever built, spread across two continents. Thousands of antennas in South Africa and hundreds of thousands in Australia, with a combined collecting area of 1 square kilometer. When it comes online around 2027 to 2028, it will be revolutionary. Current telescopes detect a few bursts per day. The SKA could detect thousands, maybe tens of thousands. With that many detections, patterns that seem impossible to find today will become routine. Questions unanswerable now will have statistical solutions. The next generation Very Large Array in New Mexico will be 10 times more sensitive, pinpointing bursts to incredibly precise locations. Space-based telescopes will observe from orbit, free from Earth's interference. And artificial intelligence is transforming everything. Machine learning algorithms process data in real time, identifying fast radio bursts the instant they occur. SumAI analyzes hundreds of terabytes daily, automatically flagging potential bursts and distinguishing real signals from interference with incredible accuracy. AI is also finding patterns humans would never notice, subtle correlations, connections between sources, predictions about where bursts might occur. So what can we expect? Perfect triangulation locating bursts not just to a galaxy but to specific regions, maybe even single stars. A massive catalog. We might have 1 million bursts in 10 years. Identification of multiple source types definitively. Real-time multi-messenger astronomy with alerts going instantly to observatories worldwide. And the most exciting possibility, discovering something completely unexpected. Whenever we build better instruments, we find things we never predicted. Pulsars weren't predicted. Gamma ray bursts weren't predicted. Fast radio bursts themselves weren't predicted. We're entering a golden age. The next decade will reveal questions we haven't even thought to ask yet. So here's my question for you. What do you think is causing these mysterious bursts? Are they all from magnetars? Or is there something else out there we haven't found yet? Could there be multiple types of sources producing similar signals? Could some of them be from phenomena we haven't even theorized about? Drop your theories in the comments below. I read every single one, and honestly, some of the best discussions happen there. If this cosmic mystery captured your imagination the way it did mine, hit that like button. It really helps more people discover these kinds of videos. Subscribe to the channel and turn on notifications, because we're going to keep exploring the universe's biggest questions. Next week, we're diving into magnetars themselves, those cosmic monsters with magnetic fields that can erase your credit cards from the distance of the moon. Share this video with someone who loves space, who asks the big questions, who looks up at the night sky and wonders what's out there. Join this community of cosmic explorers, because the universe isn't just something to observe, it's something to understand together. Remember, the universe is not only stranger than we imagine, it's stranger than we can imagine. And that's exactly what makes it worth exploring. I'll see you in the next video. Keep looking up.